This slidecast deals with reasoning about programs, and we're going to talk about assertions and loop invariants. Now, formal verification of programs is an active area of research in computer science, and it involves the use of tools to prove that a function or a program is correct. So it's desirable to prove the correctness of a program, but we usually can't do this. So in practice, formal verification is used more as a documentation tool and to enable a programmer to reason about a program. So in this section, we're going to talk about two concepts related to this, assertions and loop invariants. Now, assertions are logical statements about a program that are asserted to be true. Many times they're just written as comments in a program. Now, preconditions and postconditions are a kind of assertion statement. We've talked about those earlier, where the precondition is something asserted about the state of the program, usually the input parameters before the function is executed, and the postcondition is all about the state when the function finishes. Here is a search function. This is the one that we have seen before, and the assertion at the conclusion of the search function is that all elements were tested and the target was not found. And if we reach this point where we're going to return a -1, that's the assertion. Because if we had found a target, we would have returned here earlier and never reached this point in the code. Now, loops are a common source of program errors, and it's difficult to determine, that the loop body executes exactly the right number of times, and that loop execution causes the desired change in program variables. So programmers can use a special type of assertion called a loop invariant to help prove that a loop meets its specification. Now, a loop invariant is a Boolean expression that is true before the loop execution begins, at the beginning of each repetition or iteration of the loop body, and just after the loop exits. Now, it's called an invariant because we're going to define some relationship that remains true at all times. And if we can determine some loop invariant for the process and then verify that the execution of a C++ loop preserves this invariant, then we can have confidence that our loop's correct. So a proposed invariant for a search loop that finds the first occurrence of a target value, that's the search function we've been exploring in several slidecasts here, then if I is the subscript of the array element that we're testing in the loop, then for all k, where k is less than I and greater than or equal to 0, then x sub k is not equal to the target. So here's another way of saying it. For all non-negative integer values of k that are less than I, the kth element of x is not equal to the target. We start at the beginning of the array and we search through at ever-increasing indexes. And if we're searching at a certain location, the assumption is that all the prior locations, the search failed. So let's verify that this is an invariant. So the invariant must be true before the loop begins. So before execution, I would be 0, and there's no non-negative integer less than 0, so there's no possible value of k, and thus no value of k such that x sub k is equal to the target. So the invariant must be true before the loop execution begins. If we're starting at the first element, there aren't any early elements that could contain the target. Now, at the beginning of each repetition of the loop, we're comparing x sub I to the target during the loop, and we're executing if we found it. Now, if x sub k is equal to the target for any value of k less than I, we should have found the target earlier and exited the loop and not started the present repetition. So we argue that the invariant must be true at the beginning of each repetition of the loop, because we would have stopped earlier if it wasn't. Now finally, what about after the loop exits? So we exit the loop if we go through all the array elements and we never find the target. So for all k less than the length of the array, we didn't find it, so the invariant must also be true after we exit the loop. I mean, when we exit, if we've exited the end of the loop, we didn't find it at all. So it doesn't exist in any entry in the array. So now that we have an invariant, we write a loop that preserves it. So here is the invariant for all k such that k is less than I, greater than or equal to 0, and x sub k does not equal to the target. So let's show that this loop preserves the invariant. So variable I is initially 0, and the invariant is true before the loop repetition begins. And then prior to each loop repetition, the invariant must be true for the current value of I, or we would have executed a return statement earlier, for any k less than I. So the loop exit occurs only when the loop condition fails, when I is equal to x underscore length. Now this only occurs if we didn't find the target anywhere in the array. So x sub k not equal to target has to be true for all k less than x length, and the current value of I, which is x length. So the loop invariant is still true. And when the loop ends, the invariant is still true, but the loop repetition condition is now false, and the loop repetition condition is this conditional right here, that I is less than length. So we could combine the loop invariant and then the negation of the loop repetition condition to create this assertion. So the assertion, this part of the assertion is the same loop invariant that we had up here, and plus now we have the negation of the loop repetition, namely that I is now greater than or equal to x length. Now, proving that loops are correct, this is a topic of computer science. Ideally, we'd like to write an assertion that's a loop precondition and a postcondition, and then prove that the postcondition assertion follows from the precondition, and then we could have then we'd have proof that the loop is correct. Now, assertions written as comments, they're valuable for people to understand the program who are reading the code, but the programmer has to check that the actual code manually. Now, C++ has an assert macro. It's defined in the cassert header file, and this gives the assertion some teeth. Namely, we can use this macro to generate a code that checks and verifies the assertion at runtime. So the assert macro calls an internally defined function, and it prints an error message and terminates the program if the asserted condition is not true. And different implementations can vary a little bit, but here's the idea. The syntax for this assert statement is just the keyword assert, which is a function call where we pass an expression as a parameter, and this expression needs to be a Boolean expression, and if it's evaluated to true, execution continues, and if it evaluates to false, then we write an error message and abort. And this can be very valuable for you as you reason about your code and identify assertions. Rather than simply putting them in the comments, you can use this assert macro so that the system verifies that it's always true at runtime. And then immediately when you've got an assertion that fails, the program can print information, and then you can immediately go to that location and determine whether you have an error in the code or whether you had an error in understanding in trying to explain what conditions should hold at that point in your code. So this could be a really valuable technique to quickly find flaws in your logic and in the design of your program. And that brings us to the end of this Slidecast.